Deep inside a star, where no light has ever escaped and no eye has ever looked, two protons are moving toward each other through plasma so dense and so hot that the distance between one particle and the next is almost nothing at all. The temperature there is close to 15 million degrees. The pressure is a thing with no comparison in the world of ordinary matter. And in that darkness, two particles that should never touch, each carrying the same electromagnetic charge, each pushing against the other with a force that grows stronger the closer they come, are about to do something that by the ordinary rules of physics they cannot do. They tunnel through. Quantum mechanics allows it. The boundary that should stop them is not a wall, but a probability, a smear of likelihood spread across a narrow distance, and some fraction of all the protons moving through that plasma at hundreds of kilometers per second will find themselves, without explanation, on the other side of the barrier that should have turned them back. It is not a violent crossing. It leaves no visible mark. In the deep interior of a sun-like star, this event happens billions of times every second, and each time it does, a small quantity of energy is released, not as an explosion, not as a flash that travels outward, but as a gamma-ray photon absorbed almost instantly by the surrounding plasma, its energy swallowed and redistributed and carried by infinitely slow degrees upward. This is the proton-proton chain. 4 hydrogen nuclei enter, 1 helium nucleus comes out, and the difference in mass between those 4 protons and the single helium-4 nucleus they form, a difference so small it cannot be measured by any scale or instrument in ordinary life, becomes energy. Close to 27 million electron volts of it, per reaction, released into a core that has been sustaining this process for billions of years without pause, without fluctuation, without any sign from the outside that anything is happening at all. The star does not know it is doing this. There is no knowing in a star, no intention, no effort. There is only the pressure of the matter above pressing inward, and the energy of the fusion reactions pressing outward. And between those two forces, a balance so precise and so self-correcting that it holds steady across timescales that dwarf the entire history of life on Earth. That balance has a name. It is called hydrostatic equilibrium. It means that every layer of the star is held in place, not by any solid structure, not by any rigid connection, but by the continuous opposition of two pressures, inward and outward, gravity and radiation, each responding instantly to any deviation in the other. If the core were to produce slightly more energy, the pressure would increase, the outer layers would expand a little, the density would drop, the fusion rate would slow, and the balance would return. If the core were to cool slightly and produce less, the weight of the gas above would press inward, the density would rise, the temperature would climb, the fusion rate would recover. A star breathes in this way. Each breath takes millions of years. The result of that balance is a constancy almost impossible to imagine in terms of human experience. Over the course of 1 billion years, a span of time so long that the continents of Earth have assembled and dissolved and reassembled since its beginning, a main sequence star of one solar mass will vary in its total light output by only a few percent. Its radius remains nearly the same. Its surface temperature drifts only slightly. To any observer watching from a distance, it looks as fixed and permanent as anything in the universe. The changes are there, but they are buried so deep in time that no civilization brief enough to have a history could detect them. The sun formed 4.5 billion years ago from a cloud of gas and dust that had been drifting cold and dark through space for longer still. At the moment of its ignition, the moment when the pressure at the collapsing core became enough to push protons into range of the quantum barrier, the proton-proton chain began, and the star entered the long, quiet phase of its life that it still occupies today. Roughly 10 billion years in total is what a star of this mass spends burning hydrogen in its core. The Sun is now close to the middle of that span. Half the hydrogen in its core has already been consumed, half remains. And the star burning overhead on any given afternoon carries no outward mark of either fact. In the core where the fusion happens, the helium-4 nuclei produced by each reaction do not burn. They cannot. To fuse helium into heavier elements requires temperatures close to 100 million degrees, roughly 6 times hotter than the core of a main sequence star. At 15 million Kelvin, helium is simply inert. It settles, it accumulates. Over millions and then hundreds of millions, and then billions of years, the helium produced by the chain collects at the center of the star like sediment, settling slowly to the floor of a still pool, grain by grain, layer by layer, building upward in a quiet and accumulating mass, while the hydrogen burning above it continues unchanged. The helium core does not glow. It does not burn. It is a growing region of dense, hot, inert matter at the very center of an active star, and from the outside, there is nothing to see. The light that leaves the stellar surface on any given day was not produced today. The photon that escapes the sun in a single 8-minute journey through the vacuum of space was produced in the core somewhere between 10,000 and 170,000 years ago. It was not produced by any single reaction, but emerged from an uncountable series of absorptions and re-emissions, each one redirecting the energy a little, scattering it randomly in all directions, the energy performing a kind of long wandering walk outward through the dense plasma of the radiative zone, a walk so slow and the plasma so packed that it takes those tens of thousands of years to reach the surface. By the time it leaves the star, the reaction that produced it has long since been forgotten by the plasma that hosted it, and the helium nucleus left behind by that reaction has long since been buried under more helium, layer upon layer, year upon year. This is the interior life of a main sequence star. Not dramatic, not fast. A slow nuclear fire burning in a self-regulating core, surrounded by layer upon layer of dense plasma, each layer receiving energy from below and passing it upward by radiation or by slow convective currents. The whole enormous structure held in balance by a gravitational force that has not changed in 5 billion years. The surface, when the light finally reaches it, is hot enough to glow white and yellow in the visible spectrum, and the photons that escape pour outward in all directions at the speed of light, crossing the space between the star and its planets in the time it takes to draw a few slow breaths. There is something restful in this constancy. The star does not strain. It does not surge. It holds its fire at the precise rate that keeps its own structure intact, and it does this without intention or awareness across spans of time that have no human name. Long before the first cell divided on a young and cooling Earth, this process was already underway. Long before the first animal opened an eye to the light, the proton-proton chain was running in the solar core. It ran through every age of the planet that preceded this one. It runs now. And in an ordinary continuation of everything that has happened so far, it will continue for another 5 billion years. But the helium is still accumulating. Every reaction that converts 4 hydrogen nuclei into one helium-4 nucleus adds to the growing inert core at the center of the star. The process is slow enough to be invisible across any timescale a civilization might span, but it is continuous and it is relentless, and over billions of years, it produces a result that cannot be undone. The fraction of the core composed of hydrogen, the fuel, is slowly decreasing. The fraction composed of helium, the ash, is slowly increasing. These two facts are as simple and as inevitable as the filling of any container fed by a slow and steady source, and the star has no mechanism to prevent them, because the star has no mechanism to prevent anything. It is not a machine with parts that can be replaced or adjusted. It is a gravitational and thermal equilibrium, and the equilibrium changes as its fuel changes. The inert helium core, growing over billions of years, does something specific to the structure of the star. A region of pure helium cannot sustain the fusion that keeps the star's interior pressure high enough to balance gravity. As more and more of the core's hydrogen is converted to helium, the fraction of the core capable of fusion shrinks. The temperature at the very center continues to rise as the core contracts slightly under its own weight, but the zone where hydrogen is still present and still burning retreats outward, becoming thinner, becoming a region rather than a core, becoming a shell rather than a center. For most of the main sequence lifetime, this transition is imperceptible. The star adjusts. Hydrostatic equilibrium is maintained. The surface temperature and luminosity drift only slightly. Nothing observable changes, but deep inside, the geometry is shifting. The active burning zone is migrating outward. The inert helium region at the center is growing. The structure that has held steady for billions of years is slowly, quietly changing its internal architecture, and the change, once it begins, does not reverse. The core contracts as its hydrogen depletes. Gravity, which was balanced by radiation pressure, finds that the pressure opposing it is weakening, and so it pulls inward, and the core grows denser, and denser matter is hotter matter, and hotter matter burns what fuel remains more intensely. This is the same self-correcting feedback that stabilizes a main sequence star, but now it is working against a diminishing fuel supply, and the corrections it makes are no longer able to fully compensate. The luminosity of the star rises gradually. Over the 10 billion years of a solar mass star's main sequence life, it brightens by perhaps 30 or 40% from its initial luminosity, slowly enough that none of the life on any planet orbiting it would live long enough to notice, but measurably over geological time. Meanwhile, the photons produced in that contracting, intensifying core still take tens of thousands of years to reach the surface, still emerge as the same pale yellow light they have always been, still carry no message outward about the slow changes happening far below. The star's face remains the same. Its depth is changing. There are places in the sky where this deep constancy can be seen at scale, not in one star but in thousands, gathered together in ancient clusters where all the stars formed from the same cloud of gas at roughly the same time. In such a cluster, the main sequence stretches out in the color magnitude diagram like a long bright road, and the stars on it represent billions of years of quiet hydrogen burning spread across many different masses and ages. The heavier stars have already left. The lighter ones are still there. Each one is doing, in its own core, exactly what the sun is doing, building helium, slowly, without outward sign. But the ones at the turnoff point, the ones at the exact place where the road begins to bend away from the main sequence, are doing something slightly different. They are the stars that have reached or are approaching the moment when the core's hydrogen is not merely depleted, but genuinely exhausted, not running low, not diminishing, gone, and the process that kept the star stable for billions of years has, in those stars, lost its foundation. In the deepest part of the star, the proton-proton chain slows. The density of available hydrogen fuel in the core has fallen below the threshold at which the reaction can sustain itself. Fusion does not stop all at once. It does not extinguish like a candle suddenly snuffed. It fades. It dims over millions of years, each reaction occurring less frequently as the pool of available protons thins, each gamma-ray photon produced carrying a little less cumulative energy into the plasma above, the pressure that had held the core stable for billions of years beginning, so slowly, to ease. The core, no longer fully supported, contracts. It contracts under the weight of everything above it, the weight of the entire star pressing down, and as it contracts, it heats. This is not a new behavior. It is the same behavior the protostar showed at the very beginning, when the gas cloud first collapsed and the rising temperature eventually triggered the first fusion reactions. But now there is no hydrogen in the core to ignite. The temperature rises, but there is nothing there to burn. Above the core, however, the temperature is still rising. And just outside the exhausted helium center, where the last thin layers of hydrogen remain, where the fuel has not yet been consumed, where the advancing edge of the depletion zone has not yet arrived, those hydrogen layers find themselves at a higher temperature than ever before. The contracting, heating core below them is driving the temperature upward, and hydrogen at the right temperature burns. A shell ignites. Not the whole core, not a broad central region, a thin shell surrounding the inert helium center, where the temperature has just crossed the threshold that allows the proton-proton chain to run. The hydrogen there begins to fuse. And because this shell is hotter and denser than the core was in most of its long stable years, it burns with an energy that is not matched by anything in the star's prior history. The shell becomes the star's dominant energy source. The star, which spent billions of years burning quietly and broadly in its center, has now concentrated its energy output in a thin ring of nuclear fire, and the ring is burning fiercely. From the outside, nothing yet has changed. The star's surface temperature is the same, its size is the same, its color in the sky is the same. The photons escaping the stellar surface today were produced tens of thousands of years ago, and they carry no information about what is happening now in the interior. There is a delay written into the physics of the radiative zone, a delay of 10,000 to 100,000 years between what happens in the core and what the surface can know about it. The light now leaving the star was produced before the shell ignited. The surface is still showing the world what the star was, not what it is becoming. But inside, the transformation has begun. The inert helium core, surrounded by the burning shell, continues to grow in mass as the shell deposits more and more helium into it. The shell advances outward through the hydrogen above it, consuming fuel as it goes, its ashes falling inward to join the growing helium region below. The core contracts further. The temperature in the shell rises further. The energy output increases. And the vast envelope of plasma above the shell, the enormous outer layers of the star that make up most of its volume, begins to respond to the increased energy flux pushing up through it. This is the subgiant transition. It is not an event. It is a phase, a long, gradual, internally complex rearrangement of a star that has spent billions of years in one configuration and is now, almost imperceptibly at first, entering another. The star is leaving the main sequence. It has not arrived anywhere new. It has only finally left what it has been and the quiet constancy of its deep hydrogen-burning years is ending not with any outward sign visible to a distant eye, but in the physics of its interior, where the geometry of burning has changed, and where the change, once begun, will not stop. A star like the Sun, 5 billion years from now, will have reached this point. Its core hydrogen will have been depleted. The helium ash that accumulated silently over all those billions of years will have grown into a structure dense and inert at the star's center. The shell burning around it will have just ignited, burning more fiercely than the core ever did, and the first tentative adjustments in the outer layers will have just begun. To a distant observer watching that star from another system, the star will look almost exactly as the Sun looks today. The differences will be real but subtle: a slightly larger radius, a marginally greater luminosity, changes detectable only with precise instruments, not visible to an unaided eye. The star will not know it has crossed a threshold. Nothing in its physics recognizes a boundary between what it was and what it is becoming. There is only the continuous working out of gravity and pressure and temperature and the availability of fuel, the same physics that governed every moment of the main sequence, now operating in a configuration that is slowly, irrevocably different. And yet the crossing is real. The long quiet prime is over, the helium core is growing, the shell is burning, and something in the deep interior of the star, invisible, unfelt, unrecorded, something in the thin ring of hydrogen now consuming itself around an inert and compressing center, has set in motion a sequence of changes that will, over hundreds of millions of years, reshape the star from its core to its outermost atmosphere and alter everything about it that can be seen from across the galaxy. But that is not yet. That is distant. Right now there is only the star as it has been, the balance, the constancy, the slow and patient fire at the center of a solar system, the same pale yellow light falling across the same orbiting worlds, the same photons setting out from the surface and crossing the surrounding space at the speed of light, the same long, quiet middle of a life measured in billions of years. The gamma-ray photons produced in the core now will take 10,000 years to reach the surface. The helium settling at the core's center settles in silence, as it always has. The proton-proton chain runs in the outer shell with a brightness the old core never knew, but the surface has not yet heard of it. The light leaving the star tonight is old light. It left the core when none of this had happened. It has been traveling outward through the plasma for longer than our species has existed, and it reaches the surface knowing nothing of the shell, nothing of the growing helium mass, nothing of the transition that has in the deepest part of the star only just and very quietly begun. The star holds its shape in the sky. It burns, it shines, and far below the surface that shines, in a place where no light escapes and no signal travels fast enough to carry the news upward before the change itself has already spread further, deep in the star, in the thin and furious shell where the last hydrogen is now burning. The long stability of a hydrogen-fusing core has given way to something else, something that has not existed in that star's interior before, something small and dark and growing at the very center, surrounded by fire, accumulating in silence, patient, the way only objects without minds can be patient, settling, pressing, waiting for a temperature that will not arrive for a very long time. The night sky does not show it. The instruments do not yet see it. The star, observed from any distance, looks precisely as it always has, as steady and untroubled and ageless as the light it sends out across the dark. Only the physics knows what has changed. Only the slow arithmetic of mass and temperature and fuel knows that the long prime is over, and that what is accumulating now in the quiet at the center of that ordinary star is the beginning of everything that comes after, unhurried, unlit, and already underway. Deep inside a star, the helium core has stopped growing. For billions of years, it accumulated in silence, each fusion event in the surrounding plasma depositing another small weight of inert ash into its center, packing it slowly denser, slowly heavier, while the star above it continued its long, patient burning. The core held its shape through all of that time, not because it was rigid in any ordinary sense, but because the pressure of the nuclear fire above it was enough to keep the entire structure in balance. Nothing in the star's vast outer layers would have told an observer anything had changed. The surface held its color, the radius held its measure, and yet, somewhere in the deep interior, the last reserves of hydrogen available to the core's own burning have finally thinned past the point of sustaining the reaction, and the fire at the very center has begun to quiet. The quieting is gradual. It does not happen in an instant. Over tens of millions of years, the proton-proton chain in the central regions has been running on diminishing fuel, the rate of fusion falling as the hydrogen concentration falls, the energy released per unit volume dropping by slow degrees while the accumulated helium grows denser around it. There is no explosion. There is no visible sign. What happens instead is a kind of withdrawal. The radiation pressure that once pushed outward from the center begins to ease, and without that outward push, the inward pull of gravity is no longer fully matched. The core, which had been held in its round, compressed shape by the equilibrium of fire and gravity, now feels that equilibrium tip. Gravity wins by a small margin, and the core begins to fall inward on itself. This contraction is not fast. Stellar structures do not move on human timescales, and the collapse of the helium core is measured in millions of years rather than in any span a person could observe or imagine in a lifetime. But it is real, and it is continuous, and as the core contracts, it does the one thing that contracting gas always does. It heats. The gravitational energy of the inward fall converts to thermal energy, and the core temperature climbs. The helium nuclei packed inside are not yet hot enough to fuse. That threshold lies far ahead, at temperatures roughly 6 times higher than what the main sequence core ever reached, and so they simply grow hotter and denser, inert and accumulating, while just outside their boundary, a new and consequential process begins. In the thin layer of gas immediately surrounding the contracting helium core, hydrogen is still present. And now, with the core heating beneath it and the pressure rising in the surrounding material, that hydrogen reaches the temperature and density needed for fusion. A shell of burning ignites. It is narrow compared to the vast scale of the star, a thin ring of nuclear fire wrapped around the core, extending outward only a small fraction of the star's total radius. But it burns with a ferocity that the old core, even in its prime, never matched. The hydrogen shell is closer to the compressed, heated core. The temperatures it operates at are higher. The energy it releases per unit time is greater and rising, and it makes the star more luminous than it has ever been. The hydrogen-burning shell can be pictured as a slow ring of fire, so thin that if the star were the size of a house, it would be no thicker than a coat of paint on the walls, and yet burning so fiercely that the light it produces outshines everything above and below it. It does not stay in place. As it burns through the hydrogen at its inner edge, it consumes that fuel, and the ash falls inward to join the growing helium core, so the shell advances outward through the star over time, moving at a rate of centimeters per year through the stellar interior, an almost imperceptible progress that nonetheless, across millions of years, carries the burning front steadily higher and further from the center. With each small advance, the shell encounters fresh hydrogen and continues its work. The increased energy pouring out of this new shell now has to go somewhere. In the old main sequence star, the structure above the core was finely tuned to the energy flowing through it. The radiation zone carried outward exactly as much energy as the core produced, and the outer envelope sat at its radius in equilibrium with that flow. Now the flow has increased, and increased substantially, and the envelope above must respond. The response it makes is the one that any heated, pressured gas makes when given the opportunity. It expands. The outer layers of the star begin to move outward. The expansion is not simple. It does not proceed as a smooth inflation like air filling a balloon. Instead, it is a complex, layered heaving, different shells of the star at different depths responding to the changed energy flux in different ways on different timescales with different degrees of coupling to the layers above and below them. Some regions of the star become more opaque to radiation as they cool and expand, and where opacity increases, radiation transport becomes less efficient and convection takes over, with vast, slow overturning currents carrying energy by bulk motion rather than by the random walk of photons. The envelope thickens and deepens and swells, and as it does, the effective surface of the star, the thin outermost shell from which light finally escapes into space, is carried further and further from the center. Over hundreds of millions of years, this process continues. The radius climbs. A solar mass star that had spent billions of years with a radius roughly equal to the Sun's present size begins to grow in earnest, and the growth does not plateau. It passes 10 times the original radius. It passes 50. The inner structure is reorganizing on every scale simultaneously, the hydrogen shell advancing, the helium core growing and compressing, the envelope above swelling outward past distances that once contained entire interplanetary systems. The star that began as a tight, hot sphere the size of a small sun becomes something immense and diffuse, a vast, dim cloud of plasma stretching outward to distances measured not in fractions of the Earth-Sun separation, but in multiples of it, at 100 times the original radius. And for a solar mass star, the expansion eventually reaches between 100 and 200 times the current solar radius. The surface of the star lies roughly at the distance from its center, where the innermost planets of a system like our own once orbited. The structure that produced this expansion contains at its heart an object not much larger than the Earth, the dense compressed helium core, a few thousandths of the star's total radius, carrying roughly a third of its mass. Around that core, the thin burning shell, and above the shell, extending outward for 100 times its own diameter, the vast, transparent, slowly drifting outer envelope that is the body of the red giant. As the envelope expands, it cools. This is simply what expansion does to gas. When a volume of gas grows larger and the same particles must fill more space, they slow, and the temperature, which is a measure of their average speed, falls. The surface temperature of a star just leaving the main sequence is close to the surface temperature of the present Sun, roughly 5,800 Kelvin, the temperature that produces the pale yellow-white light of a summer noon sky. As the envelope expands and cools, that temperature falls. It passes 5,000 Kelvin. It passes 4,000. It settles, for most of the red giant phase, somewhere between 3000 and 4000 Kelvin, and at those temperatures, the light the star emits shifts in color. The shift is not sudden, and it is not all in one direction. At 5800 Kelvin, the star emits strongly across the visible spectrum, with its peak output near the green-yellow band, producing the familiar white-yellow color of a main sequence star. As the temperature falls through 5000 Kelvin and toward 4000, the peak of emission shifts toward longer wavelengths, toward orange, toward red. The color that reaches a distant observer moves from pale gold through amber, through the deep warm orange of a late afternoon sun seen through haze, and eventually into the red-orange that places the star in the K and M spectral classes. The surface is cooler, but the surface area is so vastly larger that the total luminosity, the total energy pouring out into space per second, is greater, sometimes by a factor of hundreds or thousands, despite the lower temperature. The light of a red giant at the peak of its giant branch ascent is the light of something enormous and dim by comparison to a main sequence surface, an enormous glowing body whose surface temperature is closer to that of a candle flame than to the welding arc of the main sequence core, and yet whose sheer extent more than compensates. On the color magnitude diagrams astronomers use to map stellar populations, these stars occupy the right-hand side, cool, red extended, and climb upward in luminosity as the helium core grows and the burning shell intensifies. From very far away, a red giant in its mid-ascent appears as a deep amber star, and a careful observer might note the slight orange tinge that sets it apart from the bluer younger stars nearby. Something is changing in the interior at the same time as the outer layers swell and cool. The deepening cooling envelope that expands outward is becoming less and less transparent to the radiation trying to pass through it. In the hot, dense interior of a main sequence star, photons can travel, however slowly, however tortuously, by being absorbed and re-emitted through the plasma. In the cooler outer regions of an expanding giant envelope, the gas becomes more opaque. Atoms hold onto electrons more readily at lower temperatures, and those atoms with their electrons are far better at intercepting photons than stripped nuclei are. As a result, the radiation that has been making its way outward from the burning shell finds itself increasingly unable to pass through the material above it by the ordinary route of absorption and re-emission. Where radiation transport fails, convection takes over. Packets of hotter, denser gas rise through cooler surroundings, carrying their heat upward bodily, and cooler material sinks inward to replace them. This is what happens in the atmosphere on a hot day. The ground-warmed air rises in columns, and the cooler air above flows in from the sides, but in the giant's envelope, the scale is incomprehensible by comparison, and the time scale far longer. A single convective cell in the outer envelope of a large red giant may span a substantial fraction of the star's entire radius, dwarfing the kind of granulation visible on the surface of the present sun. The envelope becomes convective from its outer edge downward, and as the giant climbs further along its evolutionary track, the convection deepens. The deepening convective envelope is one of the most consequential changes in the star's interior, because it does not stop at the boundary of chemically unchanged material. As the envelope convects deeper and deeper into the star, it eventually reaches layers that were processed by nuclear burning during the main sequence phase, layers where hydrogen was converted to helium, where the relative abundances of carbon and nitrogen were adjusted by the CNO cycle that was contributing to fusion in the hotter inner regions of the main sequence core, where the ratio of carbon-12 to carbon-13 was altered from its initial value by the particular reactions that dominated at those depths and temperatures. The convective envelope, reaching down into these regions, begins to stir them upward. This mixing event is called the first dredge-up. It is not an explosion, and it carries no violence. It is a slow, enormous stirring, the convective currents of the outer envelope reaching downward over millions of years until they tap into the layers of chemically altered material below, drawing that material gradually upward through thousands of kilometers of stellar plasma until it arrives at the surface. The star's atmosphere, the outermost few thousand kilometers from which its light escapes, begins to change in composition as material that has never before been at the surface arrives there, mixed upward from the interior. What arrives is chemically distinct from what was already at the surface. The deeper layers contain helium in greater abundance than the original stellar material, because hydrogen was converted to helium there during the main sequence burning. They contain nitrogen enriched by the C&O cycle, in which carbon-12 served as a catalyst for hydrogen fusion, and in doing so was partially transformed into nitrogen-14. And they contain a lower ratio of carbon-12 to carbon-13 than the original stellar composition held, because the fusion reactions in those layers preferentially altered the balance between the two isotopes. All of this material now rises, carried in the slow upwelling of the convective currents, and mixes into the giant's outer atmosphere. The change is subtle. It would not be visible to the eye, even if one could stand close enough to the star to observe it. The surface remains the same vast red-orange, dimly glowing expanse it was before the mixing began, but a spectroscopist measuring the precise wavelengths of absorption lines in the star's light would see the shift. Carbon isotope ratios have changed. The abundance of nitrogen has risen slightly. The helium content of the atmosphere is a little higher than it would be for an unevolved star of the same mass. Each of these is a signature, a quiet chemical notation written into the star's spectrum by the mixing of the interior, and each one can be read by instruments sensitive enough to detect the slight differences in the strength and shape of molecular absorption features in the star's cool, rich atmosphere. The cool temperature of the giant surface makes these measurements possible in a way that they would not be in a hot main sequence star. At temperatures of 3,000 to 4,000 Kelvin, molecules can survive in the outer atmosphere. Molecules of titanium oxide, which would be torn apart by the high energies of a main sequence surface, exist stably in the giant's cooler layers, and their absorption bands leave distinctive patterns across the red part of the spectrum. Carbon-bearing molecules, carbon monoxide, cyanogen, also form, and the isotopic ratios of the carbon they contain depend on which isotopes arrived at the surface via the dredge-up. The stellar atmosphere is in this way a chemical record of the interior. The physical structure of the giant at this point in its life has a quality that is difficult to convey in ordinary terms. Consider what it means for a star to have an envelope 100 or more times its original radius, composed of gas so diffuse that by the standards of the deep interior it is nearly nothing, densities in the outermost envelope far below what we would call a good vacuum in a laboratory, material stretched so thin across such enormous volume that the total mass of the envelope spread over that entire vast sphere averages almost to nothing per cubic meter. The outer layers of the giant are not solid or even liquid in any sense. They are a vast, tenuous envelope of slowly moving plasma, lit from within by the shell far below, losing material from their outermost edge to the stellar wind that has now intensified far beyond anything the main sequence star produced. Within the deep envelope, The convective motions carry heat upward in great slow overturning flows, whose timescales are long even by stellar standards. The surface brightness of the giant, integrated over its enormous area, is dominated by the contribution of these convective cells, vast, slow-rising columns of brighter, hotter gas surrounded by descending cooler material, creating a granulation pattern on scales that would span the distance between the Earth and the Sun if one could look down on it. No observer has ever seen the surface of another sun-like star in that kind of detail, but the physics of convection in these structures is well enough understood that this picture holds with reasonable confidence. The helium core at the center of all this vast structure is compressing steadily through this entire period. As the hydrogen shell burns outward and deposits more ash onto the core mass grows, and because it cannot ignite its own fuel, the core can only respond to the growing weight above it by compressing further. The compression heats the core. The heating of the core intensifies the burning of the overlying hydrogen shell. The intensified burning produces more energy flux, which drives the envelope a little further out, which cools the surface a little more, which makes the star a little redder, a little more luminous from its enormous surface. Each step feeds the next in a long, slow, mutually reinforcing chain that carries the star up the giant branch over hundreds of millions of years. The star that began this process as a slightly fatigued version of its main sequence self, barely distinguishable from the outside, is now genuinely different. The change has crossed the threshold from internal to observable. The outer layers have drifted apart. The surface has cooled and reddened. The luminosity has climbed far above the value that would be expected for an object of the same mass, at the same age, on the original stellar sequence. A careful astronomer, comparing stars of the same age in a cluster, would see the giant branch members standing out clearly, redder and brighter, drifted off to the right and upward on the color magnitude diagram, different in a way that is not ambiguous. And yet the star is not aware of itself as different. There is nothing in the physics of the expansion that corresponds to a crisis or a threshold of any ordinary kind. The hydrogen shell burns, the core compresses, the envelope rises. These processes have been underway in some form since the core hydrogen began to thin, and they continue on the same kind of time scale, slow beyond any ordinary reckoning, patient and continuous, driven by the same forces that govern the star's entire preceding life. The expansion is not a departure from the laws that shaped the main sequence. It is those same laws operating on a structure whose internal composition has slowly, irrevocably changed. In a globular cluster, an ancient gravitationally bound system containing hundreds of thousands of stars that formed at nearly the same time, the red giant branch is visible as a distinct population. When the brightnesses and colors of all the stars are plotted together, a narrow ribbon of red, luminous stars rises steeply from the point where the main sequence bends away, and that ribbon is the red giant branch. Each star on that ribbon is at a slightly different stage of the same process, a slightly more massive helium core, a slightly higher shell luminosity, a slightly more expanded envelope. The sequence from bottom to top of that branch encodes in spatial distribution the evolution through time of a single star, the long, slow climb that takes hundreds of millions of years for any individual star plays out before the eye in the spread of many stars at different stages. The rise along the giant branch does not have a fixed speed in the sense that the main sequence life did. The hydrogen shell burning accelerates as the helium core grows. More mass above, more pressure, higher temperatures, faster burning, a more luminous shell, a more extended envelope. So the star climbs faster as it rises. The lowest parts of the giant branch just above the main sequence turnoff are populated by stars, spending relatively long times in each luminosity range. The ascent is slower there. Higher on the branch, where the core is more compressed and the shell burns more fiercely, the star moves through each stage more quickly, and the upper giant branch is less densely populated as a result. Near the very top of the branch, where the luminosity has climbed to hundreds or thousands of times the original solar value, the ascent becomes swift on stellar timescales, rapid in relative terms, though still slow by any human measure. The surface of the giant, at the upper end of its ascent, is a remarkable place by any standard of the ordinary world. The temperature is low enough that a distant observer would see it glowing deep orange-red, its color more closely resembling the sky near the horizon in the final minutes before the sun sets than the pale blue-white of a hot young star. The outer atmosphere is rich in molecules, metal oxides, carbon compounds that could not exist at main sequence temperatures. It is cool enough, far enough from the dense core, that the material here is loosely bound, and the stellar wind, the continuous slow exhalation of mass that all stars produce, has intensified in this outer, loosely held envelope to rates many thousands of times greater than the current sun's. The giant is not just expanding and cooling and brightening, it is also dissolving. The outer layers it extends so far from the center are increasingly easy for radiation pressure and the thermal motion of the plasma to lift away entirely, and the wind that flows outward from the giant's surface carries real quantities of mass into the surrounding space. Over the giant branch lifetime, this wind accumulates in a vast expanding shell around the star, an invisible fog of gas, and in the coolest outer regions where molecules can form, microscopic dust grains that condensed from the cooling plasma like frost settling on a cold surface. That circumstellar material records in its density and chemistry each phase of the star's expanding life, a growing archive written in particles smaller than the wavelength of light, drifting slowly outward at tens of kilometers per second, spreading over thousands of years into a shell that encloses the star in its own exhalations. The deepening convection and the chemical mixing it produces continue through the giant branch ascent. The first dredge-up, once initiated as the convective envelope deepens enough to reach the processed interior, does not complete in an instant, but plays out over millions of years as the boundary of the convective zone moves inward and then eventually retreats again. The surface abundances shift gradually and then gradually stabilize at new values that reflect the mixed composition. A red giant star observed near the middle of its giant branch ascent carries, in the precise ratios of its atmospheric molecules, a quiet record of everything that happened in its interior since the original formation of the star, the long hydrogen-burning main sequence, the slow accumulation of helium ash, the first structural reorganization as the core contracted and the shell lit. It is strange to consider that the surface of a star, the photosphere from which light finally escapes after the long random walk from the interior, is a kind of record. The main sequence surface was, in some sense, chemically shallow. It reflected the original composition of the cloud from which the star formed, modified only by the very slow diffusion of elements over long timescales. But the red giant surface, mixed by the deep convection of the dredge-up, reflects interior chemistry. The nuclear reactions of the main sequence phase, completed long ago in a region of the star that will never again be accessible to direct inspection, leave their signatures in the photosphere, readable to an instrument pointed at the star's light from light years away. There is something in this that repays slow consideration. The giant branch star, despite its vastness, despite the enormous slow machine of nuclear burning and pressure equilibrium that keeps it from either collapsing or flying apart, is transparent in this specific way. Its surface gives away what happened deep inside, not through any single dramatic revelation, but through the gradual, patient delivery of chemically marked material upward through the convective envelope, a process that takes millions of years and leaves its record quietly in molecular absorption lines in the star's spectrum. The outer envelope, meanwhile, continues its long drift outward. The star's radius is not yet at its maximum. That lies further along the giant branch ascent, closer to the summit, where the helium core will eventually reach the conditions needed for its own ignition. For now, the expansion continues, the cooling continues, and the star slowly takes on more of the qualities of the archetype. Its color deepens into the reddish amber band. Its surface granulation becomes more irregular and large scale as the convective cells that carry energy to the surface grow to match the scale of the enlarged envelope. The star grows slowly less like the star it was, and the transformation which began quietly in the core when the central hydrogen first thinned is now written in the light it casts across the surrounding dark. A planetary system around such a star would be experiencing something utterly different from the stable illumination of a main sequence era. The giant's luminosity is not merely greater, it is growing year by year and century by century as the helium core increases in mass and the hydrogen shell burns more fiercely. A planet that once sat in a temperate zone at a comfortable distance from the star now receives far more radiation than it did. The surfaces that were once solid may now be bare and hot. The ices that accumulated in the outer system are sublimating into gas. The outer edge of habitability, if such a concept can be extended to this phase, has moved steadily outward and will continue to move as the star climbs. But the star does not hasten for this reason. It has no knowledge of the planets it once warmed. The physics that drives its expansion cares nothing for what lies in the surrounding space. The hydrogen shell burns because the pressure and temperature at the base of the unburnt hydrogen layer are sufficient for fusion. The envelope expands because the energy flux through it has increased. The core compresses because gravity acts on mass, and the thermal pressure of a non-burning inert gas is insufficient to hold it fully against that pull. Each of these processes follows from the physical state of the matter it acts on, and each is blind to everything outside itself. This blindness is not cold. The slow, enormous change taking place in the giant over hundreds of millions of years. The expansion, the cooling, the chemical mixing, the steady upward drift of the processed interior material is as patient and indifferent as geological time, as the drift of continents, as the slow filling of ocean basins with sediment. It proceeds because the matter it acts on follows the laws that govern all matter, and those laws do not hurry and do not hesitate, and have not changed since the first stars lit in the earliest galaxies. The first dredge-up completes its work slowly, and then, as the convective boundary retreats with the further evolution of the star, leaves its permanent mark. The surface abundances settle. The helium content is a little higher. The nitrogen is a little more abundant. The carbon isotope ratio has shifted to a new value, a fingerprint of the nuclear processing that occurred during the long main sequence life, and has now been exposed, drawn upward by the convective stirring of the deep interior. These chemical signatures sit in the starlight, carried outward at the speed of light to wherever the light may travel. A spectroscopist observing the star from a distant system, with instruments sensitive enough to measure molecular absorption in the near infrared, would decode from those lines the history of the interior, not the star's origin, not its future, but the quiet chemistry of what happened in the core over billions of years and has now arrived without announcement at the surface. The information was always in the star. The dredge-up simply delivered it outward, where it could at last be read in the light the star shines into the surrounding dark. In the ancient light catalog of a globular cluster, where 100,000 stars have burned together since before the Earth existed, there is a narrow ribbon of color running up through the diagram. It is cooler than the sun, it is brighter than the sun, and it curves upward, through orange and deep red, toward luminosities that outshine the sun by factors of 500, 1,000, 2,000 times. This ribbon is not a mystery, it is a road. Every star of roughly one solar mass that has ever lived long enough has traveled it, and the ribbon exists in the diagram because the travel is slow, slow enough that at any moment, in any ancient cluster, dozens of stars can be found somewhere along its length, each one a different milestone on the same unhurried ascent. The road has a name. It is called the Red Giant Branch, and to follow it from bottom to top, from the quiet orange star just departing the main sequence toward the enormous, cool, blazing giant near its summit, is to follow one of the longest continuous transformations in the life of a star, a climb that takes hundreds of millions of years and ends at its very peak in an event that releases energy at a scale almost too large to hold in the mind, yet leaves the star's visible surface entirely unchanged. Begin at the bottom of that ribbon. The star is still recognizable. It is cooler than it was on the main sequence, and a little larger, its envelope already beginning the slow drift outward that will define its coming centuries of change. The helium core at its center is dense and dark and growing. No fusion takes place inside it. It is only compressing under the weight of everything above, growing smaller and hotter with each passing million years. Around its outer edge, a thin shell of hydrogen burns with a ferocity exceeding anything the star's core managed during its long previous life, and it is this shell, this narrow ring of nuclear fire encircling the dark helium center, that now drives the star's luminosity upward along the climb. 100 million years pass this way. The shell burns outward through the star's hydrogen reserves. The helium core beneath it grows in mass, and because mass accumulates in the core, while the core is unable to generate pressure through fusion, something else must provide support. In the main sequence star, the core burned, and the burning produced pressure, and the pressure held the weight. Now the core cannot burn, so instead it compresses. The compression itself generates heat, and the heat provides a portion of the support the burning would have provided. But the core must grow denser and denser to maintain it, contracting by degrees over millions of years, the nuclei packing tighter, the electrons between them being squeezed into closer and closer quarters. Deep inside the growing core, something is changing at the quantum level. The electrons in ordinary matter have a kind of freedom. They occupy a range of energies and positions, responding to temperature, moving faster when heated. But as the helium core grows denser, the electrons begin to lose that freedom. Quantum mechanics forbids two electrons from occupying the same quantum state simultaneously, and as the available states fill up, the electrons are forced into configurations that resist further compression regardless of temperature. The pressure they exert, this exclusion pressure, this refusal to be pushed any closer, no longer responds to heat. It depends only on density. The core has entered a state called electron degeneracy, and in entering it, the core has lost the self-correcting mechanism that keeps ordinary matter stable. In non-degenerate matter, a rise in temperature produces a rise in pressure, which causes expansion, which cools the material back down, a gentle feedback loop that prevents runaway. In degenerate matter, that loop is broken. Temperature and pressure have become strangers to one another. Heat can rise without producing expansion. Energy can accumulate without relief. This distinction matters enormously. It matters more than almost anything else in the life of a sun-like star, because the helium core is still heating, still receiving energy from the shell burning above it, still contracting and compressing, year after year and millennium after millennium, and eventually the temperature inside this small, dense, degenerate object, an object roughly the size of Earth, composed of matter so dense that a teaspoon of it would outweigh a mountain, will approach 100 million Kelvin. At 100 million Kelvin, helium fuses. Before following what happens next, stay for a moment with the object on the threshold. The degenerate helium core at the summit of the red giant branch is a thing of quiet extremity. Surrounding it, the star has expanded to tens or hundreds of times the diameter of the present sun. Its outer layers cool and diffuse, its surface glowing a deep and steady amber. The visible star is enormous, but at its center, buried under that vast envelope, is this small, dark, compressed thing, Earth-sized in a sun-sized star, dense as nothing in ordinary experience, unable to fuse and unable to stop heating. It has been building toward this moment for hundreds of millions of years. Every million-year increment of the red giant ascent has been, in a sense, the approach to this threshold. The climb up the red giant branch, read from the bottom, is the slow story of a core compressing toward the point where it cannot hold the heat any longer. The outer star, meanwhile, shows none of this. From outside, from the vantage point of any distant observer watching this star among the hundreds of thousands in its ancient cluster, the red giant near the tip of its branch is simply an extremely large, an extremely bright, an extremely cool star. Its surface temperature has fallen to somewhere between 3,000 and 4,000 Kelvin. Its luminosity has climbed to perhaps 1,000 times the sun's present output, maybe more. It glows red-orange against the dark. It is enormous and quiet, and it has been changing on the scale of human lives in no visible way at all. Nothing in its light carries any sign of what is about to occur inside it. And then the helium ignites. It does not ignite gradually. It does not ignite in the orderly, self-regulating way that hydrogen ignition proceeds on the main sequence. It ignites in a runaway. The first helium fusion reactions release heat. In ordinary matter, that heat would produce expansion, and the expansion would lower the temperature, and the temperature drop would slow the fusion, the thermostat that governs all ordinary burning. But this is degenerate matter. The heat raises the fusion rate without producing expansion, and the higher fusion rate releases more heat. The more heat raises the fusion rate further. There is nothing to stop it. The runaway cascades through the degenerate core in a fraction of a second, or in seconds, or in minutes, the exact time scale still being refined by models, and in that brief interval, the energy released in the core reaches a rate comparable to the total luminosity of an entire galaxy. Every star in the Milky Way, for a moment, is matched by this single event inside a single stellar core. None of it reaches the surface. This is perhaps the most disorienting fact about the helium flash, as this event is known, that something of this magnitude occurs, and the visible star records nothing. The energy of the flash propagates outward through the stellar interior and is absorbed by the surrounding layers. The star's deep structure is rearranged, but the light that eventually leaves the stellar surface on the days and centuries surrounding the helium flash is no different from the light that left before it. No brightness spike, no color change, no flicker. The helium flash is the loudest event in the life of a sun-like star, and it happens in perfect silence, invisible inside a cocoon of cool red light, leaving no mark on the face of the star that any observer, anywhere, could ever detect in real time. What the flash does leave is a transformation of the core's interior structure. The energy deposited in the degenerate helium finally, over the course of time, lifts the degeneracy. The core heats past the point where quantum exclusion dominates and returns to a state where temperature and pressure are coupled again. The thermostat is restored. The runaway is over. What remains is a helium-fusing core that now burns in the normal, self-regulating way of non-degenerate matter. And this core, newly luminous and newly pressurized, begins to expand. The expansion of the core changes the entire internal architecture of the star. The hydrogen-burning shell above the core, which had been driving the red giant's luminosity upward for hundreds of millions of years, finds its environment altered. As the core pushes outward, the shell's pressure conditions change, and the shell weakens. Less energy flows outward through the envelope. The envelope, deprived of the intense flux that had held it in its expanded state, begins to contract. Over tens of thousands of years, a span short by the standards of the giant branch ascent, but long by any other measure, the star's outer radius shrinks. Its surface temperature rises slightly. Its luminosity, which had climbed to near the tip of the red giant branch, falls back to something closer to 50 or 100 times the sun's current output. The star is rearranging itself. From the outside, this is a quiet contraction and mild warming, barely perceptible as a track in the color magnitude diagram, a short movement back down and slightly to the left. From inside, it is a complete restructuring of the energy budget, the shell that dominated the giant's life stepping back, the core that was dark for centuries now lit again with steady nuclear fire. This new configuration has a name. The star has entered the horizontal branch, named for the roughly horizontal track it occupies in the color magnitude diagram, where stars of varying envelope masses but similar core masses cluster at intermediate luminosities and surface temperatures. The name is deceptively calm. It describes what is, in stellar terms, a period of genuine and extended stability, a new main sequence in a sense, but burning helium instead of hydrogen. In the horizontal branch core, at a temperature near 100 million Kelvin, helium fusion proceeds through a process called the triple alpha reaction. The name points to the ingredients, alpha particles, which are helium-4 nuclei, fusing with one another in a sequence that would be impossible if the universe's nuclear physics were arranged even slightly differently. Two helium nuclei collide and briefly form a nucleus of beryllium-8. Beryllium-8 is unstable. It exists for only a fraction of a second, a timescale so brief that calling it a moment is a generous exaggeration, before it disintegrates back into two helium nuclei. Almost always, this is what happens. The beryllium falls apart before anything else can occur. But in the dense, hot interior of a horizontal branch star with enormous numbers of helium nuclei present, there is a small but real probability that a third helium nucleus collides with the beryllium-8 before it decays, and when that collision happens, the result is carbon-12. This path from 3 helium nuclei to 1 carbon nucleus is one of the primary ways the universe makes carbon. Every carbon atom in every organism that has ever lived traces its origin through long chains of stellar and planetary chemistry to a triple alpha reaction somewhere, to a moment in the interior of a horizontal branch star, or an asymptotic giant, or a more massive star burning helium in its core, when three helium nuclei found each other in the right sequence at the right density and the right temperature. The horizontal branch star, in its quiet, patient burning, is a carbon forge. It produces no visible sign of this. Its light is steady, its surface warm and orange, its behavior unremarkable to any observer watching from outside. But in its core, in the same nuclear fires that produce its luminosity, it is building the element that organic chemistry depends upon. The horizontal branch phase lasts between 50 and 100 million years. By the standards of the main sequence, 10 billion years for a solar mass star. This is brief, but it is not a moment. It is a stable, extended, self-regulating phase of stellar life, and during it, the star genuinely rests. The core is hot and burning and non-degenerate, meaning any local excess of energy produces expansion and cooling, which reduces the fusion rate, which prevents runaway. The thermostat works, the star settles, the luminosity stays relatively constant, the surface temperature holds. Compared to the long instability of the red giant ascent and the traumatic reorganization of the helium flash, the horizontal branch is quiet in a way the star has not experienced since the main sequence. Outside the burning helium core, the star still carries a hydrogen-burning shell, the same structural feature that drove the red giant ascent, now diminished in intensity and no longer the dominant energy source, but still present. Above that shell, the convective envelope that deepened so dramatically during the red giant phase is still there, still carrying energy outward by the slow overturning of vast quantities of stellar material. The star on the horizontal branch is not a simple object, but it has found a balance, and in that balance it can persist. Stellar clusters offer the clearest view of the horizontal branch as a collective phenomenon. In a globular cluster, an ancient spherical swarm of hundreds of thousands of stars, all formed at roughly the same time from the same cloud of gas, the horizontal branch appears in the color magnitude diagram as a horizontal spread of stars at intermediate luminosity, ranging from hotter blue-white objects on one end to cooler yellow-orange ones on the other. The spread in temperature across the horizontal branch reflects variation in the amount of envelope mass the individual stars retained after the red giant ascent. More envelope means a cooler, more extended star. Less envelope means a hotter, more compact one. What all horizontal branch stars share is a helium core of roughly the same mass, containing roughly the same amount of fuel, burning at roughly the same rate. The variation in their appearance is a surface phenomenon. Their cores are nearly identical. This near uniformity of core mass at the horizontal branch is a direct consequence of the helium flash itself. The flash occurs when the degenerate core reaches a certain mass, approximately 45 to 50% of a solar mass, and the conditions for helium ignition are met. Different stars arrive at that threshold at slightly different times and by slightly different paths, but all of them arrive at roughly the same core mass when they do. The helium flash, for all its hidden violence, is a leveling event. It erases the individual history of each star's red giant ascent and delivers every star to the horizontal branch with a core of nearly uniform size, nearly uniform composition, and nearly uniform fuel supply. What varies, what gives the horizontal branch its horizontal spread, is what happened to the envelope during the ascent. and that is where the star's individual history remains legible. The horizontal branch star burns steadily. Each year, a small fraction of the helium in its core is converted to carbon, and a smaller fraction of that carbon captures another helium nucleus to become oxygen. The core grows richer in carbon and oxygen and poorer in helium, slowly over tens of millions of years. This process does not announce itself. The star does not change visibly. Its surface temperature shifts slightly, its luminosity moves slightly, but the broad character of the star, a moderately luminous, orangish, quietly burning object, remains stable throughout. Think of the core during this phase as a slowly changing chemical composition enclosed in an otherwise steady machine. Helium enters the triple alpha process and becomes carbon. Some carbon captures a helium nucleus and becomes oxygen. The ratio of carbon to oxygen in the growing inert center of the core shifts across the horizontal branch lifetime, and that ratio matters. It determines the structure and composition of what the star will carry forward into its next transformation. The exact proportion depends on the rate of that helium capture reaction, which is one of the less precisely known quantities in stellar physics. Current measurements suggest that the core at the end of horizontal branch burning contains roughly equal parts carbon and oxygen, perhaps with oxygen slightly dominant, but the number is not settled with certainty. The core that emerges from the horizontal branch will become the central object of the star's final phase, and its composition, determined in these quiet tens of millions of years, matters for everything that follows. But follow nothing yet. Stay on the horizontal branch. Stay in the still amber light of a star that has found its footing after the long upheaval of the giant branch and the hidden violence of the flash. The triple alpha reaction in the core proceeds in silence, building carbon and oxygen atom by atom, nucleus by nucleus. The hydrogen shell above the core burns gently, contributing a fraction of the star's luminosity. The convective envelope overhead moves in vast, slow currents, carrying energy outward at the pace of geological time. The star is burning. The star is stable. And for the first time in hundreds of millions of years, the star is not in the middle of a crisis. There is something worth resting in here. The helium flash, that hidden galactic scale event, is over. The long, slow compression of the degenerate core is over. The runaway that could not be stopped by any thermostat has stopped itself, not by being checked from outside, but by burning its way to conditions where the check was restored. The core became degenerate because it could not burn. The flash ended the degeneracy because it finally could, and the result is a star that burns helium in a calm, self-regulating way for 50 to 100 million years, which is the natural response of a stellar core to having fuel and the freedom to use it without runaway. The ancient globular clusters still carry this story in their light. Look at the color magnitude diagram of any cluster older than about 10 billion years, and the horizontal branch is there, a scatter of orange and yellow and sometimes blue-white stars spread across a narrow range of luminosities. Each one a former red giant that has come through the flash and found this quieter burning. Among the largest and most ancient clusters, the horizontal branch is rich with stars, dozens of them visible in any careful survey, each one spending its 50 to 100 million year horizontal branch lifetime in that strip before moving on. The horizontal branch stars in a cluster are in a real sense all at the same point in the same story. They started from the same material, formed at the same time, climbed the same red giant branch, passed through the same hidden violence, and arrived here at this relative calm. The variation in their surface temperatures is a record of their individual mass loss histories, how much material each one shed as its envelope expanded during the giant branch ascent. But their cores are nearly the same. They are burning the same fuel in the same way, at the same temperature, separated only by how much of themselves they kept. In the diagram, the horizontal branch appears in what seems at first like a position of rest. The red giant branch rises steeply to its luminous tip. The horizontal branch sits below and to the left of that tip, at lower luminosity, at slightly higher temperature. The movement from one to the other looks in the diagram like a step back, a retreat from the tip, a reduction in luminosity, a slight warming, and in physical terms, that is exactly what it is. The horizontal branch star is smaller than the red giant it was at the tip. Its luminosity is lower, its surface temperature is a little higher. The envelope has contracted and the star has settled, and what the diagram records is the quiet fact of that settling. The carbon building up in the horizontal branch core is not inert in quite the same way the helium was inert in the red giant core. Helium could not fuse at red giant temperatures. Carbon in principle can fuse, but only at temperatures approaching 600 million Kelvin, far above what the horizontal branch core sustains. So the carbon and oxygen accumulating at the core's center behave for now like a slowly growing reserve, growing heavier as helium fusion continues, changing the core's composition, but not yet available as a fuel source. The star carries this growing carbon-oxygen interior through the entire horizontal branch phase without burning it. When the helium in the core runs low, when, after those tens of millions of years, the fraction of helium remaining in the central regions falls below the threshold needed to sustain the triple alpha reaction at the required rate, the horizontal branch ends. The core can no longer support itself through helium fusion. It begins to contract again, and the history of the red giant branch begins, in modified form, to repeat. A helium-burning shell ignites outside the now inert carbon-oxygen core. A hydrogen-burning shell continues above it. The star begins to climb again, to expand, to cool at the surface, to brighten on what is called the asymptotic giant branch, the second great giant phase, where the structure grows more complex and the burning more episodic and the chemical enrichment more extraordinary than anything on the red giant branch. But that second climb is a different story. What matters here, in this pause between the first summit and the next, is the stability of the horizontal branch itself. The star has crossed the threshold. It has survived the flash. It is burning helium. It is making carbon. And for 50 million years, or 100, or somewhere between, it will do so in a state of balance, its core neither compressing toward catastrophe nor expanding toward dissolution, its luminosity neither climbing toward a tip nor falling toward extinction. It simply burns. There is a quality in this that reaches beyond the astrophysics. The helium flash was an event of extraordinary hidden power, energy at galactic scale, entirely absorbed before it could reach the light, leaving no trace on the surface the star showed to the universe. And from that hidden event, the star emerged not diminished, but reorganized. The core that had compressed for hundreds of millions of years into a degenerate, superheated, runaway-prone object found in the flash its own release, and the release restored the conditions for calm. The star after the flash is not smaller in any fundamental sense than the star before it. It carries forward everything it accumulated on the red giant branch, the helium core mass, the chemical enrichment brought to the surface by convection, the memory encoded in its light of 1 billion years of quiet fusion before the climb began. It carries all of that into a new phase of burning, quieter than what preceded it, and it burns. The light leaving the horizontal branch star carries no record of the flash. The photons drifting outward through the stellar envelope, through the convection zone, through the photosphere, and into space were produced in the shell burning and in the core burning of the present phase. They know nothing of the runaway. They carry the composition of the surface, which carries the record of the first dredge-up, the ancient processed material mixed to the surface during the red giant ascent. But the flash itself left no spectroscopic signature, no luminosity spike, no color shift that would be detectable at any wavelength. This is, in a way, the deepest thing the horizontal branch demonstrates. The most significant internal event in the life of a sun-like star left no visible mark. The universe did not announce it. The star did not announce it. The energy was absorbed. The degeneracy was lifted, the core reorganized, and the star continued. Any distant observer watching that star through 1,000 years centered on the helium flash would see a red giant quietly glowing at the tip of its branch, and then, across the following tens of thousands of years, a slightly smaller and slightly warmer star settling onto the horizontal branch. The transition would be detectable in a careful survey, but the cause, the galactic scale release inside the core, would be entirely invisible. The globular cluster NGC 6752, roughly 13,000 light-years away in the constellation Pavo, has been observed long enough and carefully enough that its horizontal branch is well mapped. The stars there carry the record in their colors and luminosities. Some are bluer, hotter, stripped of more of their envelopes during the giant branch ascent. Some are redder, cooler, retaining more of their outer material. All of them, in their cores, are burning helium at 100 million Kelvin through the triple alpha process. All of them came through the flash. The diagram places them in a band, a horizontal scatter of points, unremarkable at first glance in the catalog of stellar light. Each of those points is a place where 3 helium nuclei are combining to make carbon, millions of times per second, in a core the size of Earth, buried inside a star that may span a fraction of the distance from Earth to the Sun. Each is a quiet forge. Each arrived at this burning through the same long path. The main sequence, the gradual depletion of core hydrogen, the ignition of the shell, the climb, the compression, the degeneracy, the flash, and each is now suspended in the calmer phase on the other side of all of that. The light from those stars is between 7 and 14,000 years old by the time it reaches an observer. The stars themselves are between 10 and 13 billion years old. They formed when the universe was young from the first enriched gas clouds in a collapse that built 100,000 stars roughly simultaneously from the same material. They have been burning ever since, first hydrogen, then through the giant phase, through the flash, onto the helium-burning horizontal branch, most of them by now long past the horizontal branch and into their final transformations. The diagram shows only the current state, not the history, but the history is implied in the positions, and anyone who knows how to read the diagram can follow it backward. The narrow strip of the horizontal branch in that diagram, and in every ancient cluster diagram, is a pause in a long arc. The red giant branch is the ascent. The flash is the hidden summit. The horizontal branch is the descent into a new valley, a new burning, a quieter place after the crisis. And below the horizontal branch, in the lower regions of the diagram, where the main sequence stars still burn their hydrogen in slow patience, the star that will one day climb the same branch is already taking shape, younger, less evolved, sitting quietly in its long prime, with no knowledge of the trip ahead. For now, on the horizontal branch, the star burns, The core makes carbon from helium in the careful, improbable sequence of the triple alpha reaction, one carbon nucleus at a time. The shell burns hydrogen overhead. The envelope carries heat outward through convection. The surface glows in orange light. The light travels outward in all directions, crossing the space around the star in growing spheres of diminishing warmth, carrying nothing unusual, nothing that would distinguish this star from any other moderately luminous orange star in the galaxy. Nothing in that light says, this star survived a galactic scale event inside its core and emerged from it burning quietly, in balance, at 100 million Kelvin, making the carbon that a future chemistry will depend on. The horizontal branch is the calm that follows the crisis, the still water on the far side of the storm. It does not last forever. Nothing in stellar evolution lasts forever, not the main sequence, not the giant branch, not this new burning, not the final white ember the star will eventually become. But for 50 million years, or 100, the helium burns and the carbon accumulates, and the star shines, and the light crosses the dark in all directions and arrives, eventually, unchanged at whatever is waiting to receive it. The equilibrium holds, the core is steady, the thermostat works, and the star, which has spent hundreds of millions of years climbing and compressing and finally igniting in the dark, settles now into something that resembles, from a very great distance, the quiet permanence of a star simply burning, patient, unhurried, warm, and still. The sun, at this moment, is losing itself, not quickly, not in any way that could be measured in a human life, or 10 human lives, or 10,000. At this moment, the sun releases roughly 100 trillion kilograms of plasma into space every single year, material that drifts outward through the solar system, thinning and cooling, passing the orbit of the Earth and Mars and the outer planets before dissolving into the vast quiet of interstellar space. 100 trillion kilograms sounds like an enormous quantity. Against the mass of the sun, it is less than a rounding error. At this rate, the sun would take longer than the current age of the universe to lose even 1% of itself. It breathes outward so gently that the breath is nearly nothing. But a red giant does not breathe like this. A star in the final, luminous swell of its giant phase loses mass at rates that make the sun's present outflow look like the faintest trace of vapor rising from still water on a cold morning, where the sun sheds roughly 1/10 trillionth of its mass each year. A star in the upper reaches of the red giant branch can shed 1/10 millionth, or even 100 millionth of its mass in the same span. The difference between those numbers is not merely large. It is the difference between slow evaporation and a continuous, generous, decades-long release. A star not merely breathing, but slowly, patiently giving itself away. What moves outward from a red giant in these long millions of years is not a dramatic eruption. It is a wind, diffuse, steady, invisible to any ordinary observation, but immense in its accumulated consequence. Plasma streams away from the star's extended outer layers at speeds of tens of kilometers per second, carrying with it atoms forged in the star's long nuclear history, ions and electrons, and dust grains barely larger than the wavelength of light. The wind does not roar. It drifts, and in drifting over spans of time longer than the age of the Earth, it fills the space around the star with a vast, slowly expanding cocoon of shed material, material that will persist long after the star itself has changed beyond recognition. The outermost layers of a red giant's atmosphere are, by the standards of any ordinary gas, extraordinarily thin. The density there is lower than the best vacuum achievable in any laboratory on Earth. But a red giant is so large its radius expanded to 100 or more times the Sun's, that even these tenuous outer regions represent an enormous volume of plasma, and the gravitational hold the star exerts on them is far weaker than it would be closer in. Gravity falls off with distance. The surface layer, sitting 100 solar radii from the star's center, feels a gravitational pull, far less than the same material would feel near a compact star's surface. The material is already, in a sense, only loosely held. The energy that lifts this material away comes from radiation, light pressing outward through the gas. In a main sequence star, the surface gravity is strong enough that even intense radiation cannot drive a significant outflow. But in a giant, with its vast, cool, extended atmosphere and its weakened gravitational grip, the balance shifts. The radiation field presses outward on the gas, and the gas, already weakly held, begins to move, slowly, at first imperceptibly, then steadily, over millions upon millions of years, away. There is a relation, simple in its bones, elegant in what it encodes, that describes how this mass loss operates in red giants. It connects three quantities: the star's luminosity, its radius, and its mass. A star that is more luminous, more extended in radius, and less massive loses more of itself to the wind. Each factor tells a physical story. Greater luminosity means more radiation pressing outward. Greater radius means weaker surface gravity. Less mass means that same reduced gravity over the whole structure. Together, these three quantities combine into a single number, a rate in solar masses per year that describes how quickly the star is dissolving itself into space. The astronomer Reimers, working through observations of giant stars in the 1970s, set down this relationship as an empirical formula calibrated against real stars. It carries his name, and though more refined prescriptions have been developed in the decades since, the Reimers formula remains at its core a statement of something simple and true. The most luminous, most swollen, most lightly bound giants return the most of themselves to the interstellar medium, and they do so continuously over timescales measured in tens of millions of years. In the formula's structure, there is also a single adjustable parameter, a dimensionless number, typically set somewhere between roughly a third and a half, that accounts for the efficiency with which radiation drives the outflow. Its precise value matters. A star that loses more mass on the giant branch arrives at later stages of its evolution, with less of itself remaining, and the downstream consequences cascade across its entire remaining life. But even within the range of plausible values, the fundamental picture does not change. Red giants lose mass, they lose it continuously, and the cumulative effect of that loss, accumulated over the full duration of their giant phase, is substantial. To feel the scale of what this outflow represents, it helps to hold both numbers beside each other and let the difference settle. The Sun, at this moment, loses roughly 1/10 trillionth of its mass each year. An upper red giant branch star loses 1/10 millionth of its mass each year. That is 1,000,000 times more. Over 100 million years of giant branch evolution, a span roughly equal to the time elapsed since the first dinosaurs were replaced by the first small mammals. A star losing mass at these rates would shed a substantial fraction of its entire body. The star that ends the giant branch phase is meaningfully lighter than the star that began it, not by a small correction, by an amount that reshapes its subsequent evolution, but the outflow from a red giant is not simply gas. In the star's coolest outer layers, something else is happening, something quieter, slower, and more intimate in scale than the vast plasma wind that carries it outward. Dust is forming. Near the surface of a red giant, temperatures fall below 4,000 Kelvin. In some regions of the extended atmosphere, in the very outermost shells, they fall even further, below 2,000 Kelvin, or lower still. At these temperatures, the individual atoms moving through the stellar atmosphere begin to slow enough relative to one another that they can collide and stick. Silicon and oxygen atoms pair and cluster. Carbon atoms find one another. Over time, not the geological time of mountains, but still long by any ordinary measure, these pairings grow. Grain by grain, in the loosest and most figurative sense, tiny solid particles begin to condense out of what was previously a pure gas. They are small, almost beyond imagining, a few tenths of a micrometer across, comparable in size to the wavelength of visible light, but they are solid. They are the first solid matter to form in the outflowing wind of a red giant, and their presence changes everything about how that wind behaves. The chemistry of these grains depends on the chemistry of the star's outer layers. In a star where oxygen is more abundant than carbon, as is the case for most red giants in the early stages of their giant branch evolution, the available carbon is locked away in carbon monoxide molecules, and the remaining grain-forming material is primarily silicate in character. Silicon and oxygen bond into tiny crystals, producing grains of a mineral character similar to the olivine and pyroxene found in terrestrial rocks and in meteorites. These are the silicate dust grains that form in the winds of oxygen-rich giants. In stars where carbon has been mixed to the surface in quantities sufficient to exceed the oxygen abundance, as can happen in the most evolved giant stars, the chemistry reverses. Carbon is now in excess. Carbon monoxide still forms, but there is carbon left over, and that excess carbon condenses instead into grains of graphite and silicon carbide. These carbonaceous grains are chemically distinct from silicate grains and respond differently to the radiation field around them. In both cases, once dust grains exist, they absorb light. Radiation from the star presses against them more efficiently than it presses against bare gas. The grains are accelerated outward by the radiation pressure, and, as they move, they drag the surrounding gas with them. The dust-gas coupling, the physical interaction between tiny solid grains and the plasma that surrounds them, converts the radiation field's outward push into a wind that is substantially stronger than gas alone could sustain. Dust formation does not merely accompany the mass loss wind from a red giant, it drives it. In the most luminous giants on the upper red giant branch, the presence of dust in the outflow is thought to be one of the primary mechanisms by which mass loss is enhanced to the rates described by the Reamer's formula and beyond. The grains condense in a zone not far outside the star's visible surface, where temperatures have fallen enough for solid matter to persist without being immediately vaporized by the stellar radiation. This dust condensation radius sits somewhere between a few and a few tens of stellar radii from the photosphere, depending on the star's luminosity and temperature. Inside that radius, it is too hot for dust to exist. Outside it, the grains form and are pushed steadily outward, never to return. Each grain that forms and drifts away carries with it a small piece of the star's history, atoms that were once part of the stellar interior, processed through nuclear reactions across billions of years, now locked into a solid crystal of silicate or graphite, drifting through interstellar space at speeds of tens of kilometers per second. Something else pulsates through this picture, something that gives the mass loss from red giants its particular rhythm. Many giant stars do not merely expand and radiate steadily, they breathe. not in the metaphorical sense used to describe the slow equilibrium of hydrostatic balance, but in a genuinely physical sense. They expand and contract in radial oscillations that repeat on timescales of tens to hundreds of days. Driven by complex interactions between the stellar radiation field and the opacity of the stellar envelope. In the most luminous giants, these pulsations are large amplitude events, changing the star's radius and luminosity by significant fractions of their mean values over each cycle. A pulsating giant expands outward over a period of weeks or months, its outer layers lifting away from the center of mass, cooling as they rise. Then the expansion slows, halts, reverses. The layers fall back inward, compress, heat slightly, and the cycle begins again. Each outward surge lifts gas higher into the atmosphere than it would reach in a non-pulsating star. Higher means cooler, and cooler means that material which would not otherwise reach the dust condensation threshold is briefly pushed into the temperature range where grains can form. A pulse lifts gas, the gas cools, dust condenses from the cooled gas. Radiation presses on the dust and the gas coupled to it moves outward. The next pulse lifts fresh gas into the same region where the same process repeats. The coupling between pulsation, dust formation, and radiation-driven outflow creates a mass loss mechanism far more efficient than any one of these processes would be on its own. The pulsation lifts the material. The dust condensation converts the radiation field's energy into mechanical outflow. The radiation pressure accelerates the grains and the gas they carry outward into the circumstellar envelope. In the most extreme cases, this coupled mechanism drives mass loss rates that are higher still than the upper giant branch values already described, deep into ranges where a star can lose a significant fraction of its envelope mass in a relatively short time. These are the winds of the most luminous pulsating giants, and they represent some of the most prolific returns of material to the interstellar medium in the entire life cycle of a sun-like star. All of this material, the gas, the dust, the molecules, the ions, does not simply vanish after leaving the star. It accumulates over millions upon millions of years of continuous outflow. The material shed by a red giant gathers around it in a slowly expanding shell, thickening and spreading outward at the speed of the wind. The inner edge of this shell is being constantly replenished by fresh outflow from the star. The outer edge has been expanding since the giant phase began and may now lie at distances that dwarf any ordinary astronomical scale, tens of thousands of times the distance from the Earth to the Sun in the most extended cases. The whole structure, diffuse, vast, slowly growing, is called the circumstellar envelope. The circumstellar envelope is largely invisible in ordinary starlight. The gas it contains is too diffuse to produce significant visible emission, and the dust, though solid and real, is too sparse to block the view of the star behind it in any dramatic way. But in infrared light, at wavelengths longer than visible red, felt as heat rather than seen as color, the envelope glows. The dust grains absorb shorter wavelength radiation from the star, warm up, and re-emit that energy as thermal radiation at longer wavelengths. An infrared telescope, looking at a heavily mass-losing red giant, sees not just a point of stellar light, but a warm, diffuse cocoon surrounding it, a faint, extended glow that traces the shape and temperature of the dust distribution across the entire envelope. That glow is not merely decorative. It is a record. The density of the dust at any given distance from the star encodes the mass loss rate at the time that material was shed. Denser regions indicate periods of higher mass loss. Gaps or thinnings may indicate periods of lower activity. The geometry of the envelope, whether it is spherically symmetric or elongated or structured in shells, records the history of pulsation episodes and changes in the wind's intensity over time. An infrared image of a red giant's circumstellar envelope is, in a precise and literal sense, an archive. It is the star's own history of mass loss, written in the distribution of dust across light years of space, readable by anyone with the right instruments and the patience to look. In that archive, the chemistry of the dust carries its own layer of information. Silicate grains and carbonaceous grains produce different spectral signatures in the infrared. A star that has shed primarily silicate dust through most of its giant phase, but then, late in its evolution, mixed enough carbon to its surface to become carbon-rich, would produce a circumstellar envelope with a chemical gradient, silicate material in the outer, older regions, and carbonaceous material in the inner, more recently shed shell. The boundary between these two chemical regimes, if it can be resolved by infrared observations, records the moment the star's surface chemistry changed. The envelope is a diary, written in mineral and carbon, in a language that infrared light reads clearly. There is something about the idea of this archive that invites a long, slow attention. The material now sitting in the outermost reaches of a red giant's circumstellar envelope left the star millions of years ago when the giant phase was just beginning. It has been drifting outward ever since, slowing slightly as it moves against the diffuse pressure of the surrounding interstellar medium, cooling as it loses the warmth of the stellar radiation field behind it. The atoms in those outermost grains, silicon, oxygen, carbon, iron, traces of heavier elements, were forged in nuclear processes that took place deep inside the star long before it ever became a giant. They spent billions of years inside the star's interior, carried upward to the surface by convective motions, then swept off the surface by the stellar wind, then locked into a tiny solid grain, then carried outward into space across timescales longer than the history of complex life on Earth. Now they drift, they cool, they travel, and when, eventually, perhaps in another million years, perhaps in 10 million, they slow enough to be swept up by the interstellar medium, they will join the vast diffuse reservoir of dust and gas that fills the space between stars. They will mix with material from other stars, other winds, other giant phases, and other stellar deaths. And from that mixed reservoir, in some future epoch whose timescale dwarfs even the giant branch evolution that produced them, new stars will form. The dust grains now floating in a red giant circumstellar envelope are, in the most literal chemical sense, the raw material of future solar systems. There is no urgency in this. There is no hurry. The process is patient in a way that makes geological patience look brief. The chemistry that returns to the interstellar medium through red giant winds is not chemically neutral. A star that has lived through billions of years of hydrogen fusion accumulated helium in its core, and then spent millions of years on the giant branch with a deep convective envelope that periodically mixes interior material to the surface, is returning to space, a set of elements and isotopes that is meaningfully different from the hydrogen and helium that formed the star in the first place. The winds of red giants are enriched. They carry helium, carbon, nitrogen, and traces of heavier elements. They carry isotopes of carbon and nitrogen, whose ratios reflect the temperatures and densities at which nuclear reactions took place deep inside the star, billions of years ago. Each atom in the wind is a small chemical tracer of the conditions that created it. A single red giant, over its full giant branch lifetime, may return somewhere between a tenth and half of its original mass to the interstellar medium through this steady outflow. For a star roughly the mass of the Sun, this means somewhere between a tenth and nearly half a solar mass of chemically enriched material released into space over a period of hundreds of millions to perhaps a billion years. Multiplied across the billions of red giants that have existed throughout the history of the Milky Way, this steady return of material represents one of the primary mechanisms by which the galaxy's chemical composition has changed since its formation. Red giant winds are not incidental to the story of galactic chemical evolution. They are one of the main engines of it. There is a particular quality to this contribution that differs from the dramatic, sudden enrichment of a supernova. A supernova, the explosive death of a massive star, returns material to the interstellar medium in a single brief catastrophic event, enriching the surrounding space in a matter of seconds, hours, days. The return is violent, the shockwave visible, the remnant hot and luminous for thousands of years. Red giant winds operate on a different register entirely. There is no explosion, no shockwave, no brightness, just a slow, patient, continuous outflow that persists across millions of years, enriching the surrounding medium at a rate so gradual that no single year's contribution would be measurable by any instrument, but whose cumulative effect across deep time is comparable in scale to anything the universe's more dramatic events can produce. This gradualness is the character of the red giant wind. It is the character of most of what happens in the long final years of a sun-like star. Not explosion, but exhalation. Not collapse, but slow dissolution. Not a single bright moment, but an endless series of ordinary moments, each one releasing a little more, carrying a little further, contributing incrementally to an archive of material that will outlast the star itself by billions of years. In the very outermost and most diffuse regions of the circumstellar envelope, where the wind material is oldest and has traveled farthest from the star, the density has fallen so low that the grains are no longer shielded from the ultraviolet radiation of the interstellar radiation field. Photons from distant stars, arriving from all directions, begin to break apart the molecules that formed in the wind close to the star: carbon monoxide, water, silane, acetylene. The photodissociation of these molecules releases free atoms and ions that were previously bound up in molecular form, changing the chemistry of the outermost envelope in ways that are measurable by radio telescopes sensitive to the emission lines of specific molecular transitions. Each molecule that breaks apart under interstellar radiation adds another layer to the chemical record. The envelope contains a record not just of the star's mass loss history, but of the long, slow chemical evolution of the wind material as it ages and drifts and dissolves into the galaxy around it. The transition zone where the circumstellar envelope meets the interstellar medium is not a sharp boundary. It is a gradual blending, densities declining, temperatures shifting, the chemical composition of the wind material slowly mixing with the ambient interstellar gas until the distinction between the two becomes meaningless. At some distance, there is no longer a circumstellar envelope. There is only the interstellar medium, slightly enriched, carrying within it a diffuse excess of silicate grains or carbon grains or molecular fragments that were, millions of years ago, part of a red giant's outer atmosphere. The star is still burning, far away. The envelope is still being added to, close in, but the outer edge of what was once a recognizable shell of shed material has dissolved into the larger universe, its contribution made, its identity as the product of a single star, no longer distinguishable from the general chemical fabric of the galaxy. There is something almost restful about this dissolution. Not loss in any grieving sense, but return, material moving back into the medium from which it will one day be drawn again, pulled inward by gravity into a new dense cloud, a new collapsing core, a new protostellar disk, new planets, new atmospheres. The slow breathing out of a red giant, which began as a discussion of mass loss rates and empirical formulas and dust condensation thresholds, arrives here at something simpler. A star that formed from the interstellar medium will return to the interstellar medium, not at once, not violently, but slowly over millions of years in a continuous and generous release that leaves the space around it permanently changed. The circumstellar envelope of a red giant near the end of its giant branch phase, dense enough now to glow warmly and continuously in infrared light, layered in chemistry from decades and centuries and millennia of accumulated outflow, carrying within it the chemical record of a star's entire internal history, is one of the most information-rich objects in the galaxy. It holds the history of the star's mass loss episodes, like annual rings in wood, each shell of slightly different density corresponding to a period of slightly different activity. It holds the chemical evolution of the star's surface across millions of years. It holds the mineralogy of the dust that condensed from the star's atmosphere under conditions of temperature and pressure that no laboratory has ever precisely replicated, and it glows quietly in the infrared, not brightly enough to see with the naked eye, even from nearby, not in any wavelength that a human standing outside at night would detect, but persistently over the millions of years of the giant's remaining life, radiating its accumulated warmth outward into space, cooling slowly as it expands and thins, and the contribution of new dust grains from the stellar surface becomes relatively smaller against the growing volume of the envelope. It will glow for a very long time, long after the star that produced it has moved on through subsequent phases of its evolution. The circumstellar envelope will persist as a diffuse, slowly cooling record of what happened here, in this region of the galaxy, over all these long and patient years. The wind, at this moment, still flows. Material is leaving the star's extended atmosphere right now, cooling as it rises through the chromosphere and the outer layers into the free space beyond. Dust grains are condensing in the cooler regions outside the dust condensation radius, absorbing starlight and being pushed outward by the pressure of that light, dragging the surrounding gas with them. The envelope is thickening imperceptibly by the mass of what today's wind is adding to it. The outer edge of the oldest shed material is drifting one small fraction of a kilometer per second farther from the star than it was when this paragraph began, carrying with it atoms that were part of the stellar core billions of years ago, that were mixed to the surface by convective motions millions of years ago, that were lifted off the surface by the stellar wind and locked into a grain of silicate dust hundreds of thousands of years ago, and that have been drifting outward ever since, through the dark and the cold, away from the star that made them, toward the vast interstellar medium that will one day welcome them back. The stellar wind does not announce itself. There is no sound in space, no visible shimmer at the surface of a red giant, no sign visible at any ordinary distance that anything is being released. The star appears in visible light as a point of deep orange-red luminance, immense and steady. Its outflow is invisible. Its circumstellar envelope is invisible, except to instruments designed to see in the infrared. The process by which it is slowly returning itself to space is one of the most fundamental in stellar physics, and one of the quietest in all of astronomy, a dissolution so gradual, so gentle, and so complete that it can only be fully appreciated across timescales that have no ordinary human referent at all. Somewhere in the galaxy, right now, tens of millions of red giant stars are doing exactly this. Their circumstellar envelopes are expanding, their winds are flowing, their dust grains are condensing and being pushed outward by starlight. Their chemical archives are accumulating in the infrared glowing cocoons around them, each one a record of a single star's long final years, each one slowly dissolving at its outer edge into the interstellar medium that will carry its material forward into the next generation of stars and planets and whatever forms on them. This is how stars give back what they were given. Not with drama, not with catastrophe, but with patience and with chemistry and with the slow, continuous generosity of an outflow that never stops across millions of years in the deep and quiet dark between the stars, the envelope drifting outward, grain by grain, into the vast and ancient medium that holds everything the galaxy has ever made and will hold everything it has yet to make. Warm with the remembered heat of 1 billion long and patient suns, in the outer layers of an aging star, where the temperature has dropped low enough for the first solid particles to form, the light moves differently than it does anywhere else in the universe. It does not stream outward cleanly. It presses against grains of newly condensed dust, each grain smaller than the wavelength of a single color of visible light, and the pressure of that pushing slowly lifts material away from the star, outward, into the dark that surrounds it. The grains are the first solid things made in that part of space. They are silicate, mostly silicon and oxygen bonded together into a form that the cooling gas could sustain, settling out of the atmosphere the way frost settles from cold air onto a still surface before dawn. This is how the star begins to return itself to the galaxy, not in a single event, not in one long breath, but in this quiet, continuous giving, outward grain by grain, molecule by molecule, across spans of time so long that the slow dispersal has the quality of stillness. The star that does this is a giant of the asymptotic branch, one of the last configurations a sun-like star will hold before the long, cool, final dissolution begins. It is enormous, where the sun, at its present size, fits comfortably within the orbit of Mercury. This star fills the space out to the orbit of the Earth, or beyond. Its outer layers are cool by stellar standards, 3,000 Kelvin or less in places, cool enough for chemistry to happen in the atmosphere, for molecules to form, for dust to condense, for the distinction between gas and solid to exist at all. The interior is still burning. 2 shells of nuclear fire are still active deep within, but the envelope above them is diffuse and vast and slow, and the outermost skin of it is exhaling continuously into space. In the thin, cool outermost region of the envelope, individual atoms of silicon and oxygen drift together. The conditions for bonding are met. A grain forms, a particle smaller than a bacterium, smaller than a human cell, smaller than most things that have names. It is solid matter, crystalline in structure, floating in the outer atmosphere of a star. And when the light from below presses against it, as light presses against anything it cannot pass through, the grain is nudged. Slowly at first, then steadily. The radiation from the stellar interior is intense, even filtered through hundreds of millions of kilometers of tenuous gas. Against the tiny mass of a dust grain, it is enough. The grain begins to move outward. The gas around it moves with it. The dust carries the gas, and the gas carries more dust, and the outflow deepens, A wind develops not the modest wind of the present-day sun, which sheds roughly 1/10 trillionth of its mass each year, a figure so small it is almost nothing. This wind is 100,000 times stronger. On the upper branch of the asymptotic giant, a star may lose 1/10 millionth of a solar mass each year, year after year, for millions of years. The cumulative outflow is enormous. It spreads in every direction, slowing as it goes, thinning as it spreads, until it forms a vast expanding shell of gas and dust around the star, a circumstellar envelope, invisible in ordinary light, warm and faintly glowing in the infrared, recording in its density and its chemistry everything the star has released over the long pulsing years of its final phase. The envelope grows. It is not uniform. The star does not exhale smoothly and evenly. It pulses over periods of hundreds of days to 1,000 days or more. The star expands and contracts in a rhythm that is not quite regular, but is persistent and deep. Each outward surge lifts fresh gas into the upper atmosphere, where it cools, where dust condenses, where the outflow intensifies for a time before settling back. These oscillations are visible from outside the star as changes in brightness, the star brightening and fading over months and years in a pattern that the variable star observers of the past 3 centuries cataloged and named, and in some cases came to love, in the way that patient observers come to care for things they have watched for a long time. One of those stars has a name that has been used for 400 years. It was called Mira, the wonderful, by Dutch astronomers who noticed it brightening and fading in the constellation Cetus long before anyone knew what a star was made of. Mira is what a late asymptotic giant branch star looks like from a few hundred light-years away. It is an oxygen-rich giant, pulsing with a period of roughly 330 days, fading from naked eye visibility down into obscurity and brightening back again with each cycle. From where it stands, it loses material into space at a rate that has built an enormous envelope around it, stretching for a distance that, if it were placed at the center of our own solar system, would extend far beyond the most distant planets. The envelope is not just gas. It is chemically enriched, carrying the products of the nuclear burning that took place deep inside the star, brought to the surface through the slow mixing of convection, and now dispersed outward into the medium between stars. That mixing is one of the central facts of what an asymptotic giant branch star does. Deep inside, the structure is precise and layered. At the center is an inert core of carbon and oxygen, the ash of earlier helium burning, now too cool to fuse further, a core roughly the size of the Earth, dense as the inside of a collapsed object, holding in its composition a record of everything the star has burned. Around it burns a thin shell of helium. Above that burns a shell of hydrogen. These two shells do not burn steadily or in simple coordination. The helium shell burns and exhausts itself and reignites in periodic bursts, thermal pulses, each one releasing, in the span of years to decades, more energy than the star would otherwise produce in 100 million years of ordinary operation. Each pulse sends a wave of energy outward through the stellar interior, driving the convective envelope inward and downward in what is called the third dredge-up. The third dredge-up is not a violent event. Nothing about this phase of a star's life moves quickly. It is a slow reach. The convective envelope, which occupies the vast outer regions of the star and is always churning gently, warm material rising, cooler material sinking, in the way that cream stirs slowly through a heated fluid, extends its lower boundary downward after each thermal pulse, reaching into the chemically enriched region between the two burning shells. In that intershell region, carbon-12 has been building up since the most recent helium flash, fresh carbon, newly forged from helium nuclei combining in the triple alpha process. The dredge-up carries it upward. It rises through thousands of kilometers of stellar interior, mixed in the slow currents of the convective envelope until it reaches the surface. A spectroscopist examining the star's light after a dredge-up episode would see changes in the ratios of carbon isotopes. The surface composition of the star has shifted. The interior has written its record into the atmosphere. After enough dredge-up episodes, the surface composition can shift fundamentally. A star that began as oxygen-rich, in which oxygen atoms outnumber carbon atoms in the outer layers, a condition that governs the chemistry of the atmosphere and the dust, may become carbon-rich, with more carbon at the surface than oxygen. The dust that forms in the atmosphere of a carbon-rich giant is different from the silicate grains of an oxygen-rich one. It is carbonaceous, graphite flakes, silicon carbide particles, the dark sooty material of a cooled carbon-bearing gas. Carbon stars are recognizable in their spectra by the molecular signatures of carbon compounds in their outer layers, and they are among the primary sources of carbon dust in the galaxy. The grains that condense in their winds drift outward, and eventually, over immense spans of time, become part of the raw material from which new stars and new planetary systems form. But the most patient and extraordinary work of the asymptotic giant branch is not in the carbon. It is in the slow building of heavier atoms, one neutron at a time, in the thin interior regions where the neutron flux is just enough to allow capture, but not so high as to be overwhelming. This is the slow process, the SES process, and it operates in a pocket of the inner shell region that is barely wider than a thin layer of sediment on the floor of a deep lake. The pocket forms when hydrogen mixes in small quantities into the helium-rich intershell region during the dredge-up, reacting with carbon-12 nuclei under the heat of the region to produce carbon-13. Carbon-13 is unstable against a particular reaction. When an alpha particle, a helium-4 nucleus, encounters it under the right thermal conditions, the two combine, and a neutron is released. Free neutrons are rare in nature. They decay in about 15 minutes if left alone. But inside the intershell pocket, before they can decay, they encounter the heavier atomic nuclei already present in the region, iron, and the suite of elements heavier than iron that accumulated in the star when it formed, inherited from earlier generations of stellar nucleosynthesis. A nucleus that absorbs a neutron becomes an isotope of the same element, 1 unit heavier. If that isotope is stable, it simply waits, possibly for years or centuries, until the next neutron arrives. If it is unstable, it undergoes beta decay, one of its neutrons becoming a proton, transforming the nucleus into the next element up the periodic table. Over many such captures and decays, the nucleus climbs the table of elements. It accumulates mass and changes identity in small steps, each step separated by long, quiet intervals, the nucleus drifting through the neutron-rich intershell environment, like sediment settling in still water, each collision with a neutron nudging it 1 unit further along. The elements built in this way are not the light elements. They are not hydrogen or helium or carbon or oxygen. They are the heavy ones, strontium and barium, lanthanum and cerium, neodymium, the rare earth elements, and at the upper end of the S process chain, lead. Lead is the final accumulation point for many S process pathways, the stable terminus, where further neutron capture would only produce radioactive isotopes that quickly decay back to lead. A star undergoing S-process nucleosynthesis is quietly producing, can a layer thinner than a finger's width relative to the scale of its vast envelope, atoms that will one day be found in the minerals of other worlds, in the soils of planets not yet formed, in the electronics and the alloys and the chemistry of whatever comes after. The lead that forms in the intershell pocket is eventually mixed outward in subsequent dredge-up episodes, carried by convection to the surface, and from the surface dispersed by the stellar wind into the circumstellar envelope. It becomes part of the expanding shell. It drifts outward at tens of kilometers per second, slowing over time until the envelope has extended for distances that dwarf the solar system. The gas and dust of the circumstellar envelope will eventually disperse into the general interstellar medium, the diffuse material between stars, where it will mix with material from other sources, supernova ejecta, winds from other giants, the slow seepage from planetary nebula. And in that mixed medium, over spans of time measured in billions of years, molecular clouds will form and collapse, and new stars will ignite, and the barium and the lead and the carbon will be swept into the protoplanetary disks around those new stars. And from those disks, solid bodies will aggregate. The star does not know any of this is happening. It pulses, it sheds, it carries on burning in its two thin shells around the carbon-oxygen core that grows incrementally with each thermal pulse as more helium is converted to carbon and oxygen and deposited at the inner boundary. The core is growing, the envelope is shrinking as mass is lost to the wind. These two trends work in opposite directions, the core growing, the envelope diminishing, until eventually the envelope becomes too thin to sustain the complex burning structure. The thermal pulses cease, the hydrogen shell extinguishes. The star enters a final, brief, brilliant phase in which its surface temperature rises rapidly. The remnant envelope ionized by the intense radiation from the now exposed hot interior. The outer gas glows, but that is later, and it is brief, and before it, the long pulsing years stretch on for a span so vast that any individual pulse, any individual dredge-up episode, any single night of watching a mirror-type variable brighten by a fraction of a magnitude is almost nothing against the whole. There is something in the slowness that is hard to fully carry in language. The timescale of a thermal pulse, the interval between one helium shell flash and the next, is tens of thousands of years for a solar mass star, stretching to hundreds of thousands of years for stars that have already shed much of their envelope. Each pulse is separated from the last by a span of time longer than the entire history of modern human beings on this planet. And yet within the astronomical community's catalog of evolved stars, thermal pulses are understood as a phase of a star's life in the way that seasons are understood as a phase of a year, numerous, recurring, part of the expected structure, each one following the last in a pattern that has played out in star after star across the history of the galaxy. The galaxy is old. It has been forming stars for close to 13 billion years. In that time, countless solar mass stars have run the same progression: hydrogen to helium in the long, quiet core burning phase, the slow ascent of the red giant branch, the flash of helium ignition deep inside, the settling onto the horizontal branch, and then the long final complexity of the asymptotic branch, with its pulses and its dredge-ups and its slow, continuous dispersal of enriched material into the surrounding space. Each of those stars has added its contribution to the interstellar medium. The barium in the spectral lines of modern stars, measured today with instruments sensitive enough to detect a single element among a billion others, was built in S-process pockets inside ancient giants whose light went out before the sun was born. The carbon dust and the infrared glowing envelopes of current Mira variables will outlast those stars themselves, drifting through space for billions of years after the stars have become white dwarfs and cooled below visibility. The circumstellar envelope of a heavily mass-losing giant, visible in infrared images as a diffuse warm glow around the point source of the star, is one of the more patient archives in the universe. It holds in its structure a record of the star's entire late history. The inner regions of the envelope, closer to the star, reflect more recent mass loss. The outer regions, thinning and cooling as they expand, record episodes from millions of years ago. A careful study of the envelope's density profile and chemical composition can reconstruct in rough outline the history of how the star shed mass over time, which pulses were strong, which dredge-up episodes brought what material to the surface, how the dust chemistry evolved as the surface composition changed. The envelope is the star's autobiography, written in infrared light, slowly dispersing into the dark. In the deep interior, while the envelope is dispersing, the small carbon-oxygen core continues to accumulate. It is already dense, denser than any ordinary material, composed of matter in which the electrons are not bound to atoms, but pressed into a quantum mechanical configuration where their resistance to compression is governed not by temperature, but by the rules of quantum mechanics alone. The core is, in a meaningful sense, already a white dwarf in all but name. It is the same object that will remain after the envelope is fully shed, the same composition, the same density, the same radius close to that of the Earth. What keeps it from being called that yet is only the material still surrounding it, the two burning shells, the vast convective envelope, the expanding circumstellar cloud. Strip all of that away, which the winds are slowly doing, and what remains is already there, already formed, waiting in the center of the giant like a seed inside a fruit that is still swelling and ripening. The comparison is not perfect, and the star has no purpose, and the core has no destination it is working toward. But the density that has accumulated over billions of years of fusion, the carbon and oxygen that were once hydrogen and are now the cold, dense remnant of all that burning, there is a kind of completion in it that does not need any intent to be real. The star has been, across its long life, a machine for the conversion of lighter nuclei into heavier ones, and the core is the record of everything it converted and could not convert further. The elements it could not burn at the temperatures and densities it could reach are the ones it kept. The ones it could burn it did, until it couldn't. The Mira variables that pulse in the current night sky are stars in this condition. Each one is in a slightly different position on its long asymptotic branch ascent. Some are early in the phase, their envelopes still thick, their thermal pulses still widely spaced. Some are late, their envelopes thinning, their pulsation periods lengthening, the signs of the end visible in their increasingly deep brightness variations. From a distance, from a few hundred light years, which is where most observed Mira variables reside, they appear as red, faintly orange points in the infrared, surrounded by the diffuse glow of their circumstellar envelopes, brightening and dimming over months, completely ordinary if you do not know what you are looking at, extraordinary if you do. The night sky holds hundreds of them within the distance at which they can be seen with small telescopes. In galaxies close enough to resolve individual stars, thousands can be counted. In the infrared surveys of the Milky Way's bulge and disk, they mark the locations of intermediate age stellar populations, populations that formed 1 to 10 billion years ago from material that was itself already enriched by earlier generations of giants. The Starras process barium that a Mira variable is producing now will be in the circumstellar envelope of a future Mira variable in a few billion years, recycled through a stellar interior one more time, further enriched mixed again with fresh hydrogen that will have been fused once more into helium and carbon and oxygen in the intervening star's lifetime. The galaxy runs a slow, continuous process of chemical enrichment, and the asymptotic giant branch stars are among its primary contributors. This is what the final years of a sun-like star look like, from the largest perspective: a star that formed from a molecular cloud, itself a mixture of hydrogen and helium from the original universe and heavier elements from earlier stellar generations, burns through its hydrogen and its helium and deposits in its core the carbon and oxygen it could not further consume. It sheds its outer layers in a wind that carries those layers outward into the interstellar medium, enriched by the mixing of its long convective history, enriched further by the S-process elements built in its intershell pockets during its pulsing final phase. And then it is done, or close enough to done, that the remainder is a slow cooling of the dense remnant left behind. The star is not destroyed. It becomes smaller and quieter, and eventually invisible. But the material it released is still moving outward, still dispersing, still cooling, still seeding the space it once occupied with the products of 10 billion years of nuclear burning. The outward-moving envelope does not know where it is going. The individual dust grains within it are pressed outward by light, decelerated by the drag of the surrounding medium, heated by the general radiation field of the galaxy, cooled by their own thermal emission into the void. They are small and passive, and they drift. Over millions of years, the envelope disperses. Its inner boundary catches up with the outer boundary. The material thins below the point where it can be detected. It merges with the general interstellar medium and loses its identity as a circumstellar structure, but the atoms in it persist. The carbon is still carbon, the barium is still barium, the lead is still lead. They drift, mixed with everything else in the cold space between stars, until gravity begins to work on them again, slowly, over millions of years more, gathering them into the dense cores of molecular clouds, from which new protostars form. In those new protostars, when the density and the temperature at the collapsing core become high enough, hydrogen fusion ignites once more. The new star is not the same as the old star. It formed from a slightly more enriched medium. Its initial composition carries the S-process elements and the carbon and oxygen from the generations of giants that came before it. If it forms a planetary system, and it probably will, because planetary systems are common, because the solid-forming elements are abundant, because the physics of disk accretion is repeatable and robust, the solid bodies that aggregate in that system will carry within them the grain-by-grain contributions of those ancient pulsing giants. The iron in the body of any planetary creature that might someday live in that system will have been forged in a supernova. The carbon in its cells will have passed through the interior of a giant, the barium in its geology, the lead in its ore deposits. These were assembled, slowly, one neutron at a time, in the thin intershell pocket of a star that pulsed and shed and eventually dispersed itself across the dark, long before that creature's world existed. There is a quality of patience in all of this that the mind can approach but not fully hold. The asymptotic giant branch phase of a solar mass star lasts tens of millions of years. The S-process nucleosynthesis that occurs within a single star's intershell pocket takes place over a span of time that includes thousands of thermal pulses, each separated from the last by tens of thousands of years, each followed by a dredge-up that carries the accumulated product one step closer to the surface. The circumstellar envelope builds for millions of years and disperses for millions more. And then, in the interstellar medium, The atoms drift for millions or billions of years before gravity collects them again, and the cycle begins. Against this time scale, the observable life of a Mira variable, the 4 centuries for which human beings have been watching Mira Ceti brighten and fade in the southern sky, is not even the blink of an eye. It is less than that. It is the width of a single step on a path millions of kilometers long. And yet, within those 4 centuries, careful observers have measured the period of Mira's pulsation to a precision of days, traced the changes in its light curve over generations, mapped the structure of its circumstellar envelope in infrared, measured the abundances of East process elements in its atmosphere. In a span of time negligible against the star's own lifetime, the instruments of one small planet have read a portion of the record that the star has been keeping in its own light. The record is patient. It has been waiting for as long as the star has existed. The enriched atmosphere of a Mira variable, carrying the spectroscopic signatures of its carbon isotopes, its barium, its lanthanum. These are not new. They were written into the star's light by mixing events that took place millions of years before the first human beings sat in the dark and watched the sky. The star did not know it was keeping a record. It was only burning and pulsing and shedding, doing what the physics of its mass and composition required of it, following the long, slow path that stars of its kind have followed for as long as stars of its kind have existed in this galaxy. The night sky is full of stars in this condition, some early in their giant phase, some late, some just beginning the long climb up the red giant branch, some already pulsing near the end of their asymptotic ascent. They are scattered across thousands of light years in every direction, red and orange and infrared, surrounded by their warm and slowly expanding envelopes. They are the ordinary culmination of the ordinary life of an ordinary star. They are not rare, they are everywhere. They are what the middle mass stars of the galaxy do. And when each one is done, when the envelope is thin enough and the remnant hot enough and the outer gas ionized into a brief glowing shell, what remains is a small dense object cooling in the dark, carrying in its carbon-oxygen composition the full record of the star's entire nuclear history. It will cool for billions of years. It will not reignite. It will fade from white to yellow to orange to red, on a time scale longer than the current age of the universe, dimming by fractions of a magnitude per billion years, until it is too faint to see. But the material it released, the carbon and the oxygen and the silicon and the S-process heavy elements, the dust grains and the gas molecules in the dispersed circumstellar envelope, that material is already gone, already moving, already out in the cold interstellar space, already beginning its slow gravitational gathering into the next chapter. The star gave what it had to give. It burned for 10 billion years in the quiet equilibrium of its main sequence life. It swelled and enriched and pulsed for millions more. It shed its outer layers in a wind that carried everything it had made outward into the galaxy. And in the end, what the star leaves behind is not nothing. It is carbon, it is oxygen, it is the slow and patient chemistry of the S process, barium and lead, and rare earth elements drifting through the cold between stars. It is the material from which the next generation of solid worlds will form, and the generation after that, the material cycling through star after star, becoming richer in heavy elements with each pass through a stellar interior, accumulating over the long history of the galaxy into the complex chemistry that solid planets carry. The giant stars that burn and pulse and shed and dissolve in the night sky tonight are not ending, they are giving. The distinction matters, and the dispersed envelope of a Mira variable expanding at tens of kilometers per second through the surrounding dark, is not loss. It is the galaxy's long, slow, patient work of enrichment, carried out in billions of separate stars over billions of years, each one contributing its particular mixture of elements to the common pool. The asymptotic giant branch star is one of the most prolific contributors. It is the stage in a star's life when the chemical work of that star is most fully realized, when the mixing is deepest, the enrichment is greatest, the output is most generously dispersed. In the cool outer layers of an aging giant, in the quiet hours of its pulsation cycle, between one outward surge and the next, the dust grains drift in the extended atmosphere, some already moving outward on the slow wind, some still condensing from the gas, basma forming tonight. If tonight is a word that applies to a star whose night is 10,000 years of relative quiet between pulses, the grains are small and dark and slow. The light from below presses against them. They move outward, carrying with them the molecular record of the star's long interior life, the carbon-13 ratios that record the dredge-up events, the barium that records the SEN process, the oxygen and carbon in their ratio that records whether this is a giant that has crossed the threshold from one chemistry to another. They drift. The star continues to burn in its two thin shells. The core beneath the shells grows, infinitesimally denser. The envelope above the shells thins, fractionally, with each year's worth of outflow. The pulsation continues. The brightness varies over its long, slow period, brightening as the star swells, fading as it contracts, each cycle leaving behind a little more enriched material in the expanding envelope. The envelope continues to grow. The infrared glow of it continues to spread outward into the dark around the star, faint and warm and patient, carrying everything. The space between stars is not empty. It holds the accumulated breath of every giant that has shed its envelope into it since the first stars formed and lived and died. It holds dust grains that are older than the sun, inherited from stars that burned out before our solar system existed. It holds the S-process barium from Mira-type variables that pulse their final pulses before the Earth had cooled enough to hold liquid water on its surface. All of this is in the cold gas between the stars, mixed and drifting, slowly gathered by gravity into clouds, the clouds slowly collapsing into new stars, the cycle running on at its own vast and unhurried pace, the chemistry of the galaxy deepening by increments so small in any given generation of stars that no single star's contribution is more than a whisper, but across billions of years and billions of stars, the accumulation is everything. Every grain of silicate in every rocky world, every carbon bond in every organic molecule, every heavy element in every ore deposit on every solid planet under every star in this galaxy. The giant gives what it has, the galaxy keeps it, the dark between stars holds it gently and for as long as it takes, and the dust drifts on, quietly, carrying the star's long work outward into the still and patient dark, long after the light of the star itself has faded below the threshold of sight, long after the last pulse, long after the last trace of the envelope has merged into the surrounding medium and the star has become something else, something smaller and cooling and quiet. The grains drift. The elements persist.